of say head is p and not coming head is 1 minus p, so what would be the outcome of this actually? So this is going to be say 1 minus p, okay, so first of all this value is going to be 0, x of tt is going to be 0 multiplied by the probability of tt, so it's going to be 1 minus p times 1 minus p and 1 minus p square. Plus this guy is going to be 1 because there is one head in it. So 1 multiplied by the probability of t head, so it's going to be 1 multiplied by p multiplied by 1 minus p. And similarly for this, 1 multiplied by p multiplied by p multiplied by 1 minus p. And the final one is, I have 2 and p multiplied by p, so it's going to be p squared. Okay. The final outcome that you get is what you call 2p minus 2p squared. So this is really going to be 2p minus 2p squared plus 2p squared, so the average is really 2p. So this is really the expectation of x. Okay. And if you try to calculate the expectation of x through say numbers, so what would be the expectation of x? So it takes the value 0, 1, 2, so 0 multiplied by the, what is the probability of 0? So it's 1 minus p square plus 1, so 1 multiplied by, what is the probability that you're gonna get exactly one head? So you have to do what you call this 2 choose 1 times p and 1 minus p, and plus what 2 times what do you call 2, the other value that it takes is 2 times what do you call what are the probability of both coming head is going to be 2 choose 2 times p square. So again you get the precisely same answer, 2p. Okay. So make sure that you understand this definition. Okay, this is strange looking definition, is not really strange actually, but it's an interesting way to write the expectation. Why I am interested in this proposition actually. So I want to keep this fact and this fact in your head, and I want to prove a corollary to the previous proposition. So it's a very interesting kind of a corollary. So it says that if you have sum of expectations, sum of a random variable, then the expectation of the sum is the sum of the expectations actually. In other words, if you want to compute the expectation of z, so I can, do it directly, or the other way could be that, okay, compute the expectation of x and expectation of y, and then add the expectations actually. Because the expectation of sum is the sum of expectations. This is what is the interesting thing. Next interesting thing. So here's a quick corollary to previous result. Quick corollary to previous result. So for random variables, x1, x2, xn, these are discrete random variables, all the expectation of the sum I equal to 1 to n, xi is equal to the sum of the expectations I equal to 1 to n, expectation of xi, so the expectation of x1 plus x2 plus x3 up to xn is equal to the expectation of x1 plus expectation of x2 plus expectation of xn. So here's a proof of doing it actually. Give this sum a name, so let's call this sum z actually, xi. Now, what is the meaning of v being equal to sum of the random variables? You mean this, ठीक है, z बराबर है sum of random variables के, इसका क्या मतलब है? That is, इसका मतलब ये है, take any omega from the sample space and compute z of omega. This would be same as, okay, computing the xi of omega and summing them up. So this will be equal to the z of omega for each omega. Okay? Now let's compute. So if I want to compute this, I really, इसका मतलब ये है कि I just want to compute the expectation of z. Now what is expectation of z by the theorem? This means that I have omega from the omega, z of omega multiplied by the p of omega. Okay. But the z of omega is what? The z of omega is the sum of these xi's of omega. So I can rewrite this expression as sum from omega in omega and sum from I equal to 1 to n, okay, xi of omega multiplied by the p of omega. This is what it is going to be. ठीक है जी. And what? So I can open this sum. I can write this as that, okay, sum over omega in omega. मैं कह सकता हूँ कि this is same as if I write it explicitly. So it's x1 of omega plus up to plus xn of omega multiplied by the p of omega. ठीक है. And if this is the case, in other words, we can switch these sums actually. That's what I want to do. So if this is the case, then I can write this as the sum of the sums is, so this sum is going to be omega in omega x1 of omega times p of omega plus so on and so forth, sum in omega xn of omega p of omega. Now what is this? I mean, if you see, this is precisely expectation of x1, the definition of expectation of x1, plus so on and so forth. And what is this? This is precisely by the previous definition. This is expectation of xn. Okay, and hence you can write this as this is the sum from I equal to 1 to n expectation of xi, and you know, this is what that you wanted to prove. Okay? तो यहाँ से नतीजा क्या निकलता है? नतीजा ये निकलता है that if you want to compute the expectation of the sum of two random variables, this is same as you compute the expectation of x and compute the expectation of y and add them. Okay, so this is what it really means. So let's do some examples, some interesting simple applications of these results that you can get what out of these simple results. So here's an example 9c from Ross. So this says that the it says that find the expected value of sum obtained when n fair dice are rolled actually. Okay? N fair dice are rolled. So find the expectation of the sum. So what do you mean by? So you have n fair dice, ठीक है? n छक्के हैं आपके पास, and you all roll them, ठीक है? अब हर fair dice के केस में you're gonna have some average. So the question is, what is the net average of n rolls n dice being rolled actually, ठीक है? तो हम क्या करेंगे, हर जो डाई रोल की जा रही है उसके आउटकम को हम एक नाम दे देते हैं रैंडम वेरिएबल एक्स। फर्ज करें xi, जबकि I जो है is 1 2 3 to n है, ठीक है? is the outcome of outcome of ith die, ठीक है? यानी आपने जो ith die पहली die है उसके आउटकम जो भी आती है वैल्यू 1 2 3 4 5 6, उसके आउटकम को मैंने नाम दे दिया xi x1। दूसरी डाई जो रोल हो रही है उसके आउटकम को मैंने नाम दे दिया है x2 and so on and so forth, ठीक है? ith die. So what values xi can take? So obviously, you know, 1 can show up, 2 can show up, 3 can show up, and 3 4 5 and 6 can show up actually, ठीक है? 3 5 6 can show up. Now हमें जो मालूम करना है वो क्या करना है कि भाई इन सारी जो ये डाइस एन रोल की गई हैं इनकी एवरेज क्या होगी, यानी इनकी ऑन एवरेज कितनी व्हाट आउटकम दीज एन डाइस विल प्रोड्यूस एक्चुअली, ठीक है? सो अगर x इज रिप्रेजेंटिंग दैट सम तो इसका मतलब यह है कि x1 के आउटकम को सम कर दें x2 के आउटकम के साथ और xn के आउटकम के साथ, ठीक है? So x1 is outcome of the first die, x2 is outcome of second die, and xn is outcome of nth die, or x is the outcome of sum of all values of the numbers that showed up in die actually. और हमें करना क्या है, हमें इसकी expectation calculate. So we have to kind of calculate the expectation of x. So अगर आप ये expectation of x calculate करना चाहते हैं, so we have this corollary that tells you that okay, if you want to compute the expectation of this, you need to compute the expectation of x1 and x2 and xn. इन सब को calculate कीजिए and sum them up. So what would be the expectation of xi? So the expectation of xi, I could be 1 2 3 up to n, is going to be xi कौन सी वैल्यूज ले रहा है 1 2 3 4 5 6, इन वैल्यूज को मल्टीप्लाई कर दें इनकी corresponding probabilities के साथ. So it's going to be like 1 times 1/6 plus 2 times 1/6 plus so on and so forth, 6 times 1/6, and the outcome is going to be what? So the outcome is going to be 7/2. ठीक है? So expectation of x क्या होगी? So what is expectation of x1? So it's 7/2 plus 7/2 plus 7/2. So it's like 7/2 is being added n times. So the outcome is going to be 7/2 n. This is really the average value that shows up on n fair dice actually. So n could be your chosen number. Okay? So such kind of examples are going to be used extensively when we're going to do our theory of stochastic processes, the course on stochastic processes. So this is the fundamental, these are the fundamental facts that we need to keep in our mind, practice, and solve problems. Okay, so what next? Let's move on to the chapter number 5. So let's move on to the chapter number 5. So the chapter number 5 is about the continuous random variables and how to do what we did in discrete case random variables, how to do the same kind of stuff in case of the continuous time random variables actually. So the next is the chapter 5. So next is basically the continuous time random variables. Okay. So in our previous extensive study, we kind of studied, you know, some of the examples. We did kind of the theory which was more kind of related with the discrete kind of randomness. Okay. So the randomness in which the outcomes appears as discrete objects. Okay. Now the randomness is always not discrete actually. So for example, so it could be continuous as well. For example, so what could be the continuous time random quantities questions actually. So for example, waiting times, okay. So waiting, say for a bus to arrive at a stop. Okay. So imagine you are waiting for a bus to arrive at a stop, then what could be what would be your waiting time actually? So your waiting time is going to be a continuous quantity. So it's, so what do you mean by that? So you mean by that either maybe you don't need to wait at all, maybe as you go on to the bus stop and you catch the bus. Maybe you need to wait for the 1 minute, or maybe you know you need to wait for 1.25 minutes, okay, or maybe 5 minutes or 10 minutes or 15 minutes. So wait is a continuous thing actually. So waiting time is a continuous thing. So any kind of waiting time is a random continuous object actually. So it's a continuous time randomness. What could be some other examples? Say evolution of, say, price of a stock actually. Okay, so if you take a particular stock, so its price goes, you know, always up and down. It moves up and down instantaneously. Okay, it's a random quantity. So price of a particular stock, say Google's stock, is a random quantity. Okay, so it goes up or goes down. So this going up and going down depends basically on the demand and the supply. Okay, so it depends on the demand and supply of what do you call the stock actually. Okay, it could also depend on say the political situations. So for example, many of the stocks, the stocks of the oil companies are crashing in these days actually, in the days of the COVID-19. So they are going down, but they are continuously kind of evolving. So you know, going down, going up, and going down, and going up actually. So the evolution of price of a stock So price of a stock is a random quantity, but it's a continuous time random quantity actually. Okay. What could be another quantity? So for example, age of a person. Okay. So, you know, death is absolutely uncertain. Okay, so you never knew that when someone is going to die. Well, we are going to die. Okay. So the age of a person or anything is basically is a random quantity. Okay. You can also say for example, life of a machine. Okay, so you buy a machine, and for how many times it is going to work actually, so you have no idea. You might have a guarantee up to 2 years. Okay, so it can happen that okay, it can break down even before 2 years or after 2 years. It can work, you know, for a longer period of time or for the shorter period of time. So the life of a machine, life of a person is really a random quantity. But these random quantities are continuous actually. Okay, are continuous. So there can be many more examples actually where the randomness appears in a continuous fashion. So what is our next objective? Our next objective is to build some theory for the continuous random variables actually. Okay, continuous random variable. So we are going to start with the way we did in case of the discrete actually random variables. For example, if you give this random variable a name actually, so x represents the waiting time for a bus to arrive on a stop. So what could be the waiting time to arrive bus on the stop actually? So it really depends on the stop. So imagine it's 0 to say 15 minutes. So now x previously that was taking the discrete values is now going to take the values in the interval. So x lies in the interval. So the waiting time lies between 0 to 15 minutes or any minutes actually. Evolution of a stock price, who knows? So it could be 0 and say between say $1,000 actually. So this is really the price of a particular stock actually. So it can take any value between this. Even 1,000 is a fuzzy word because you never knew that how high it is going to go or how low it is going to go actually. For sure it's going to be above 0. Okay. Age of a person. So if I give this quantity a name x, then what could be the potential age of the person actually? So it could be say 0. So in other words, a person can die immediately after the death actually. So it has almost 0/8 of the age. Or maybe maximally, what could be the potential age for a person actually? So maybe I'd say 120 actually years. So 0 to 120 is really the age of a person actually. Okay. Life of a machine, you can also write it as that, okay, 0 to say 10 years, it depends on really the machine. Okay, so it could be, so what would be the meaning of 0? That okay, maybe the machine doesn't work in the first place. What could be other examples? So it's not necessary that you should always take non-negative values, you can take also negative values. For example, you can have, okay, so the temperature, so x is the temperature of say a region Okay, so say Sukkur in an air atom. एक साल में what could be the potential temperature of Sukkur atom? ठीक है? Not Sukkur. Let's take for example, say Islamabad. Okay, so the temperature can also go negative. Okay, so it's a random quantity. Temperature is a random quantity, and it's a kind of a random quantity that continuously evolves. It just goes up and down all the time. So what would be the temperature of say Islamabad in an air? So say you can say inverse situation. So for example, in our experience, so the worst it can go from say 5 centigrade to maybe 50 centigrade actually. Okay, degree centigrade. Then for example, this could be the value, okay, that this random variable x takes that represents the temperature of an air actually. So what I want to get through these examples is that, as in case of the discrete random variables, we kind of thought of different random quantities. जैसे हमने वहाँ पर किया जी different random quantities के बारे में सोचा, और फिर हमने सोचा कि अच्छा वो क्या potential values ले सकती हैं, and then we talked about their probabilities and so on and so forth actually. ठीक है? So the random quantities can be what we call this time. So I hope it made some sense to you. So let's do next what? Let's build some theorem. So what would be a continuous time random variable? So the continuous time random variable is going to be a random variable that is a map from omega, okay, into R, but now x does not take discrete values, but x takes values in an interval actually, a to b, where a to b could be anything. Okay, could be they could be finite numbers, they could be, say, a and b could be infinite, so it could be minus infinity to infinity, so it can take entire, all real line value, could be some finite interval, but it's going to be intervals actually. Okay, not necessarily always open intervals, it could be, closed intervals as well, or semi-open and semi-closed interval, or semi-infinite intervals. So it's a kind of a map actually. So now